Hello everybody and welcome to today's lesson on finding angle measures and number of sides in polygons. This is the first lesson in a rather short unit on polygons and transformations. And today's objectives are we will be able to classify polygons and we'll be able to find interior and exterior angle measures. And we will also be able to find the number of sides of a regular polygon given the measures of interior and exterior angles of that polygon. In order to do that, we need to first talk about what is a polygon. A polygon is a closed plane figure. It is formed by 3 or more line segments, which we also call its sides. Each endpoint of a side is what we call a vertex, and no more than 2 vertices lie on a segment. So let's use these definitions to determine which of these figures are polygons. Polygons are closed plane figures. And if we look at this figure here on the right, this is not closed. So that is not a polygon. They are formed by 3 or more line segments. And when we say line segments, we mean something that is straight. It's a straight line, not curvy like this one here. So this is not a polygon because it's not made up out of segments. Each endpoint of a side is a vertex, and no more than 2 vertices are on a segment. So what that would mean is, for example, if we have a figure that looks like that, then we have a segment here, for example, and that segment actually has 3 vertices, and in that case that would not be considered to be a polygon. All the other ones that we see here are polygons. But now we need to look at them a little bit more closely and differentiate between convex and concave polygons. A polygon is called convex if no line containing a side also contains an interior point. If we trace a line along the side of the polygon and that line doesn't contain interior points, then we call it convex. But look at this other polygon here next to it. If I take, for example, this line and I keep tracing, then at some point I get to the interior of the polygon, and that is not convex. And that is essentially what concave means. A concave means not convex. So essentially think about it. You trace over a side and the line does not go into the polygon. What does that mean for our last polygon here, our triangle? That triangle is also convex because if we traced over any of its sides, we will never get to the interior of that triangle. Now let's talk about the angle measures of a polygon. First of all, the interior angle measures. And in order to do that, we need to use the concept of a diagonal. A diagonal is a segment joining 2 non-consecutive vertices. Vertices, that's the plural of vertex. We've used this word just a minute ago. Non-consecutive essentially means not next to each other. In our figures down here, we're supposed to draw the diagonals of each polygon below from one vertex only. and then determine the number of triangles created in each of these polygons. Starting with our first here on the left, which has 4 sides, so it's a quadrilateral. We're starting from this point, but we're not tracing to the point next to it, to the right or down here. We are tracing to a non-consecutive vertex, and there's only one that we can trace to, and this is the one. Here's our diagonal, and what that does is that cuts our quadrilateral into 2 triangles. So we get 2 triangles here. Now let's do the same thing with our polygon over here. I'm going to start over here. This is our first non-consecutive vertex. Here's another one, and that gives us a total of 1, 2, 3 triangles. Starting from here, we get 1, 2, 3 diagonals, and 1, 2, 3, 4 triangles. And in our last figure here, 1 diagonal, 2 diagonals, 3 diagonals, and 4 diagonals, making 1, 2, 3, 4, 5 triangles. Why are we using triangles? Because at this point we know a lot more about triangles than about other polygons. And one particular thing that we know about is that the interior angles of a triangle always add up to, and I can hear you say it, 180 degrees, right? So if we look at this triangle here with 3 angles, and all these angles also are connected to the vertices of our quadrilateral, the interior angles add up to 180 degrees. And then we have another triangle right next to it, and that triangle doesn't have to be similar or congruent or anything like that, but it also has 3 angles, which I'm going to mark with different marks. But no matter what these angles may be, they add up to 180 degrees. So let's go to our table and mark down what we have found out so far. We're going to use this table to classify polygons, and basically what that means is to name it by the number of sides. A polygon with 3 sides is what we call a triangle. If we have 4 sides, we call it a quadrilateral. Quadri stands for 4, and lateral for sides. A polygon with 5 sides is what we call a pentagon, and you, I'm sure, know the building in Washington, D.C. that has 5 sides. That's also called Pentagon for that very reason. If it has 6 sides, we call it a hexagon. And all these parts of the name come from the Greek words of the numbers. With 7 sides, we have a heptagon. 8 sides, we got an octagon. With 9 sides, we got a nonagon. 10 sides gives us a decagon. And just think about decade or other words like that. Decathlon, that always means 10. If it has 11 sides, then we have 2 different names for it. We can either call it a hendecagon or an undecagon. With 12 sides, we call it a dodecagon. And then beyond 12, we don't give them any individual names anymore. We just call them by the number of sides and followed by the word gon. And if it has n sides, we call it an gone. So our triangle, as we said, has 3 sides, and there's only one triangle that fits inside it. Duh. So the sum of the measures of the interior angles, as we know, in a triangle is 180 degrees. A quadrilateral with 4 sides, and as you could see in the picture above, we were able to trace a diagonal and make 2 triangles inside. And looking at those triangles and their interior angle sums, we realized that then we have 2 times 180 degrees, which is 360 degrees, as the sum of the interior angle measures. Our pentagon up there gave us the possibility to create 3 triangles, so we would have 3 times 180 degrees, which is 540 degrees as the interior angle sum. The hexagon, we had 4 triangles, 4 times 180 degrees, which is 720 degrees. And our heptagon, that was the figure to the right, let us draw 5 triangles. 5 times 180 degrees is equal to 900 degrees. And I'm sure by now you guys see the pattern, right? From the number of sides to the number of triangles, how did we get there each time? Yes, exactly, by subtracting 2. And then we take that number of triangles and multiply it by 180 each time to get to the interior angle sum. That being said, I would like you to fill out the rest of the table yourselves now and then check with me later. And also think about what is the rule that you can use for the n-gon, where the number of sides is just n. Go ahead, stop the video and fill it out and check with my work afterwards. So hopefully you got to the same results here. The number of triangles, of course, is always 2 less than the number of sides, and multiply that by 180, and this is what you get for the interior angle measures, the sums of them over here on the right. Now for the n-gon, we just can create a rule. The rule is n minus 2. That's the number of triangles multiplied by 180. And we're going to leave it like that here in the box on the right. I'm not going to distribute the parentheses. And the term n-gon is really just a generic way to classify n-sided polygons. So every time we know the number of sides, we can replace n by that number. For example, a polygon with 14 sides is called a 14-gon. And now this brings us to the polygon interior angle theorem. After all the work we did in the table before, the polygon interior angle theorem says the sum of the measures of the interior angles of a convex n-gon is n minus 2 times 180. And look at you guys, you figured out that formula all by yourselves. Highlighted, this is very important. You need to remember that, and we're going to be using that a lot. Just like in these 2 examples, for example, down here, use the polygon interior angle theorem to solve for x. Now, we do have our table, but if we didn't have that table, we would need to do the work ourselves. So we need to start by finding out how many sides does this polygon have. Here in example number 5. And sometimes it's easier to actually count the angles than the sides, and it has to be the same number anyway. So counting the angles, we get 1, 2, 3, 4, 5. So this is a pentagon. Therefore, n is equal to 5. Using our polygon interior angle theorem, we can therefore say 5 minus 2 times 180, 3 times 180, which is 540. And that is the sum of all the interior angles. So we know that these 5 measures here have to add up to 540. So let's add all the like terms together so we can create our equation. We got 2x plus 5x plus 5x, so 12x, and we got 90 plus 90, which is 180. 12x plus 180 has to be equal to 540. So let's first subtract 180 from both sides, and we get 12x is equal to 360. Divide both sides by 12, and that gives us x is equal to 30. I'm sure you guys can now do example number 2 yourselves. A little hint: count the angles to determine what type of polygon you have, then find the interior angle sum, and then create your equation. Now stop the video and do the work yourselves. Hopefully you came to the same result. We got a quadrilateral with 4 angles, 4 sides. That means that our interior angle sum is 360 degrees. And when we add up all our expressions here, we get 7x plus 3 is equal to 360. And we solve this equation by first subtracting 3 on both sides and then dividing by 7 on both sides to get x is equal to 51. Well done, you guys. Of course, we can also use the polygon interior angle theorem and apply it backwards, as in these examples here. The sum of the measures of the interior angles of a convex polygon is given this time. Classify the polygon by the number of sides. So we need to find the number of sides and use the sum which is given. The sum of the interior angle measures is 1440 degrees in example number 1, and our formula is the sum is equal to n minus 2 times 180. So now we're going to take our 1440 degrees and substitute it in for the sum, and then we're going to solve this equation for n. First, we need to divide by 180, and we get 8 is equal to n minus 2. No more parentheses needed at this point. And now we're gonna add 2, and we get 10. 10 is equal to n. And this means that we have a decagon. This is a decagon. So take a minute now and think about what we did algebraically to our formula, to our equation, and use that to create a shortcut. We took our sum and we divided it by 180, and then we added 2, right? We took 1440 divided by 180, and then we added 2, and what we got was 10. So that's a shortcut to get to the exact same point. You can either do it algebraically, solve the equation step by step, or use your shortcut and you will get the same answer. And that being said, now go ahead and do example number 4 yourselves, and afterwards check your work with my work. So your sum of the interior angles was 2160, and whether you did it algebraically here step by step, or whether you did it using the shortcut in the bottom, you will get n is equal to 14, and that means we have a 14gon. No more specific names for that large number of sides, we just call it 14gon. Alright, so much for this, and now go ahead and watch the second part of this tutorial.